Hello everyone, and welcome back to my channel. This is Vishnu Manjipudi, and I am glad that you are all here. Today, I will be talking about the stars and bars method, also commonly referred to as the balls and urns method, in combinatorics. So first of all, what is stars and bars? Well, as I said earlier, stars and bars is a combinatorial method that can be used to count the number of ways that some indistinguishable items can be placed into a certain amount of distinguishable groups. So let me elaborate on that. So let's say we have n groups, okay? And we have k indistinguishable items. Okay, so the groups also have to be distinguishable. So then stars and bars tells us the number of ways we can distribute these k items among the n groups. Now, let's first derive the method and see why it's called stars and bars. So we have n groups, okay? Let's just say we have n equals 3, and we have k items, so let's just say k equals 2. So we can derive this formula by looking at a problem. So if n equals 3 and k equals 2, we can set the problem as how many ways are there to distribute 2 chocolates among 3 children. Okay, so how would we do this? This is where stars and bars comes in. So basically, imagine the chocolates are little red dots. So we have 2 chocolates. Now imagine that we have 2 sort of divider folders like this. These divider folders divide the group of chocolates into 3 parts. This part here on the left, this part in the middle, and this part on the right. So each of these 3 parts corresponds to one of the children. Let's say this is Alice, this one is Bob, and let's say this one is Claire. Okay, wrong. Okay. So then we can place these 2 chocolates in these 3 groups, i.e. people in this case, to find out the number of ways. Now, how do we count these ways? We have 2 partitions and we have 3 chocolates. And the thing is, we actually allow for some partitions to be empty. So let's say we have these 2, right? These 2 partitions, we can see that this area over here is actually empty, which means that Claire gets no chocolates, whereas Alice and Bob each get 1 chocolate. So this is a condition of stars and bars. We have that number of items per person, so per group, is greater than or equal to 0. This is an important restriction to consider, especially in problems, because there can sometimes be problems where you need to have at least 1 item per group. So let's look at something like that. So let's say we have how many ways to split let's say 5 chocolates among 2 children such that each child gets at least 1 chocolate. Now, to do that, we don't really have much intuition on that, so let's first begin by solving one of these standard problems. Now, once again, we have 2 partitions, which is equal to 3 children minus 1, and we have 2 chocolates here. Now, how many ways can we arrange these? Well, if you think about it, it's the same way as arranging a word with 2 different letters. Let's say a chocolate represents the letter C, and a partition represents the letter P. So, as you can see here, this is equivalent to the number of ways to arrange the word CPCP. And that, of course, is the 4 letters in the word choose 2 P's. Because this is the same way as having 4 blanks and choosing 2 places to put P's, which is 4 choose 2. So we can choose these 2, we can choose these 2, etc. Now, 4 choose 2 is equal to 4 times 3 divided by 2 times 1, since it's 4 times 3 times all the way down to 2 plus 1, and then 2 times 1 times all the way down to 1. And this is simply equal to 6. So we're done with our simple problem. Now, let's try to generalize this result. So, how many ways? So we have how many ways so we have n children and we have k chocolates. Well, let's try to replicate what we saw over here. Now here we saw that the number of partitions is equal to 1 minus the number of children. So in this case, we have n children, right? But then we subtract 1 to get n minus 1 partitions. Now, how many chocolates are there? Well, that's already given. We have k chocolates. So now, we can think of this problem as the number of ways to rearrange the word P dot 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 P, where there are n minus 1 P's, and then we have C, where there's K C's. And now, like we saw before, here we just sum the number of chocolates and partitions, right? Because that's the total number of letters in the word. And then we chose the number of partitions because that represents how many ways to arrange the word. So this is just equal to how many total partitions and chocolates are there? There's just n plus k minus 1. Choose n minus 1 partitions. And this can also be written if you choose to choose k chocolates out of the n plus k minus 1 words. That's equal to n plus k minus 1 choose k. Alright, so now that we've gotten an intuition for this problem, let's try working on this problem where there's at least one chocolate. So let's get a bit more of a clear screen. So we have, so how many ways such that each child gets at least one chocolate. And we're going to use the same example as the previous case, like same numerical example. So we have n equals 5 and k equals 3. So we first think of using our formula from before right here. However, this formula wouldn't actually work because each child gets at least one chocolate, whereas this formula over here assumes that each child can have no chocolates. So how do we resolve this issue? Well, since we know that there's 5 children, we can just write them out. So we have child A, child B, child C, child D. Actually, wait. This over here is supposed to be n equals 3, k equals 5. So we have child A, child B, and child C. Okay? And we have 5 chocolates. So we think about reducing this condition so that each child can just get at least 0 chocolates. But since there's at least one chocolate, what we can do is just give them the chocolate right from the get-go. So we can just give each of them one chocolate, and now each of them already has at least one chocolate. Now we just remove all those chocolates that we just picked from our set. Now, this is the exact same scenario as before, except instead of having 3 people and 5 chocolates, we now have 3 people and 2 chocolates. And now we can either use our logic or derive it from the formula. This time I'm just going to use the formula. So we have n equals 3, k equals 2 in this case. So we have a result of n, which is 3, plus k, which is 2, minus 1. Choose n minus 1, which is 3 minus 1. This is equal to 4 choose 2, which is equal to 4 times 3 divided by 2 times 1, which itself is equal to 6. And now we have solved this problem. Now finally, let's create a generalized formula for this case as well. So we have how many ways such that let's just say n children get k chocolates among them, while each kid needs at least m chocolates. Alright, so at least let's just say m chocolates per kid. Now, we can see here, in this case, we first gave 1 chocolate for each of the 3 kids. So in this case, we give initially, since we give m chocolate per child, we give m times n chocolates in the beginning, which means that we actually have k minus m times n chocolates when we actually use stars and bars. So if we have k minus m times n chocolates, let's just write this as k minus m n, we have new k. K is equal to k initial minus m times n. We have n is equal to n initial. I'll just label these all as I. We can use our stars and bars formula. So we have, as we said up here, we have n plus k minus 1, which is n I plus k I minus m times n I. Then we have another minus 1. Yep, we have another minus 1. All over n minus 1, which is n sub I minus 1. And that's it. We've just figured out the number of ways. Now for this, once again, we have to impose another restriction, which is that m times n is less than k, and for the initial values. So now that we've cleared that, let's try doing some example problems. So here we have the 2003 AMC 10A problem number 21. So it reads, Pat is to select 6 cookies from a tray containing only chocolate chip, oatmeal, and peanut butter cookies. There are at least 6 of each of these 3 kinds of cookies on the tray. How many different assortments of 6 cookies can be selected? Now, at first this may seem daunting because this is a problem number 21 on the AMC 10. However, as you can see, this is not a very difficult problem. So, since we're trying to use stars and bars, what are the groups that we want to choose and what are the items that we want to choose? Well, we have that the 3 different types of cookies could potentially be our group. And these 3 types are chocolate chip, oatmeal, and peanut butter. And these are groups. Now, what are items? Well, we can see that we need 6 cookies from the tray. So, we have that the cookies are the items. And we're also given that there are at least 6 of each of the cookies. So this means that since there's at least 6 of each of the kinds of cookies, and we can already choose only 6 cookies, that means we can essentially ignore the number of cookies. So let's see. We have 6 chocolate chip, 6 oatmeal, and 6 peanut butter. And we want to choose 6. Now, remembering our stars and bars argument, we need to have 3 minus 1 or 2 partitions. Since we only select 6 cookies, we just need 6 cookies in the stars and bars. And again, there is no restriction on which cookies we can take, because the problem doesn't say so, and there's no restriction on the minimal amount of cookies as well. Additionally, as we noted earlier, we can actually, any arrangement will work because that we're given at least 6 cookies of each, and as such, even if we pick all of our cookies from a single category, those cookies won't run out. So, from our stars and bars, we again see that, let's see, there's 6 cookies, right? And so let's first find n, of course. So we have n is equal to 2, right? Because we have 3 minus 1, since there's 3 types of cookies, and we always subtract 1. Now, what's k? K here is the number of cookies we choose. Well, here we select 6 cookies, so k is equal to 6. And now, finally, since there's no restriction, we can just solve the problem, either using our formula or using our intuition. Here, I'll do both. So, you can see that we have 6 items. We have 6 plus 2 equals 8 items. So, we have 8 items. And then, we choose 2 of those items, since there's 2 partitions. So it's 8 times 8 choose 2, or 8 times 7 divided by 2 times 1, which is equal to 28 ways. Now, we could have also just used the formula, which is n. Here we actually have n is equal to 3. So we could have used our formula, which is n plus k minus 1, choose n minus 1. This is equal to 3 plus 6 minus 1, choose 3 minus 1, which is equal to 8 choose 2, which, as noted earlier right here, is equal to 28. Now, looking back at our choices, we can see that 28 is choice D, and we are done with this problem. Now, let's do one final example problem, just to drill in understanding. So now we're moving on to example number 2, which was also the 2018 ANC 10A problem number 11. The problem reads, when 7 fair, standard, 6-sided dice are thrown, the probability that the sum of the numbers on the top faces is written as n over 6 to the 7th power, where n is a positive integer. What is n? So here we have a probability problem that is on the intersection of counting as well. So we know that probability of an event that's not what it is. Yikes. Okay. So we know that the probability of an event, so we have an event, is equal to number of occurrences or number of successes, if you want, divided by the number of total. Alright, so here we have number of occurrences divided by number of total. So let's first calculate the number of total. We have that number of total is equal to 6, because there's 6 ways for the first dice, times 6 because of the multiplication rule of counting, and there's 6 other ways, and this goes on and on for the total of 7 times, once for each dice, so there's 7 sixes. And this, from exponential notation, is just equal to 6 to the 7th power. So n is just, since the number of total is equal to 6 to the 7th power, we know that n is just the number of occurrences. And we can calculate that using stars and bars. So in this case, we actually have a restriction. That's because each dice, so let's say we have a dice, it rolls between 1 and 6. Now, here we already have a minimum restriction, and we know how to deal with those. However, we also have a maximum restriction, and we don't know how to deal with those. In fact, the only good way to deal with maximum restrictions is to k-squared count. However, we don't really want to do that. So let's check if we can actually use stars and bars. Well, we can just check if k minus m times n is less than or equal to max. So this inequality is very helpful because it basically does what we're intuitively going to do. We assign the minimum value to each of the elements and see how much is left over. So here you have 10, k is equal to 10, minus m, which is 1, times n, which is 7, which is equal to 3, and lo and behold, 3 is less than or equal to 6, which means we can use our stars and bars formula. So we derived up here that the formula is equal to, so the number of ways is equal to n, which is 7, plus k, which is 10, minus m times n. In this case, we have m is equal to 1, and n is equal to 7, and then all of that minus 1, and then we have to choose n minus 1, which is 7 minus 1. And this is equal to, this expression over here is equal to 9, and this expression on the bottom here is equal to 6. So we have 9 choose 6, which is equal to 9 choose 3, since 6 plus 3 is equal to 9. 9 choose 3. And that is equal to 9 times 8 times 7 divided by 3 times 2 times 1. And this is end up equaling to, once you cancel out common factors, we result with 84. And looking back at the problem, we see that 84 is choice E, and we are done with this lesson. Thank you so much for watching this video. It really means a lot. Please don't forget to like, share, and subscribe, as well as click the bell icon. As always, if you have any questions, comments, or concerns, please comment down below or email me at steamaspirations@gmail.com. Once again, thank you so much for watching, and this is Vishnu Ranjapudi signing off. Bye!